Have you ever tried to build a sorted list that dozens, maybe hundreds of threads can hammer on at the same time without the whole thing just grinding to a halt? Yep, it's one of those classic, really tricky problems in concurrent programming. Well, today, we're going to dive deep and dissect an absolutely brilliant solution, a high-performance, lock-free priority queue for Kotlin Multiplatform. It promises to be concurrent, bounded, and unbelievably fast. Let's dig in and see how it pulls it off. All right, here's our game plan. First, we're going to lay out the core problem we're trying to crack. Then we'll get into the weeds of the architecture, which uses this really clever combo of a data structure called a Treap and atomic operations. From there, we'll walk through exactly how a lock-free insert works, beat on it with some performance benchmarks, and then, this is the cool part, we'll explore a wild application in on-device vector search. To wrap it all up, we'll cover the guarantees and the big takeaways. So, what's the actual challenge here? I want you to picture it. You have a whole swarm of coroutines, all trying to jam elements into a single sorted collection that also has a fixed size. How in the world do you manage that chaos without just completely killing your performance, or even worse, corrupting your data? You know, the usual solutions just don't cut it. The simplest approach, slap a mutex on it. But that's like turning a 4-lane highway into a single-lane bridge during rush hour. It just serializes everything and destroys your throughput. Okay, what about something from the Java standard library, like ConcurrentSkipListSet? Well, it's lock-free, which is great, but it's unbounded. If you want to enforce a size limit, you have to add an external lock, and you're right back where you started. And a standard priority queue? Forget about it. Not even thread safe. So this is the classic trade-off, right? You can have this simple mutex that bottlenecks everything, or you can have the fast, unbounded structure that can't manage its own size. It feels like you can't have your cake and eat it too. But what if you could? It turns out the secret sauce is a really elegant combination of a persistent data structure, the Treap, and something called compare and swap atomic operations. Let's pull back the curtain and look at the architecture that makes this whole thing tick. It really is an elegant solution to a very, very thorny problem. Okay, so the heart and soul of this library is a data structure called a Treap. Now, if you're not familiar, just think of a binary search tree. But instead of all these complex, rigid rules for keeping it balanced, it uses randomness. It's a beautiful mix of a binary search tree's ordering and a heap's priority property. And here's the real kicker. It's a persistent data structure. That means when you change it, you don't actually modify the original. You get back a new version, sharing most of its structure with the old one. It's incredibly efficient. So why a Treap? Why not a good old red-black tree or an AVL tree? Well, it all comes down to simplicity and how well it plays in this persistent copy-on-write world. I mean, a red-black tree has 5 gnarly invariant rules you have to maintain. An AVL tree is constantly tracking heights. A Treap, on the other hand, has just one simple rule. A parent's randomly assigned priority has to be bigger than its children's. That's it. This randomness gives us probabilistic O-log n balance, and its rotations are super localized, making it absolutely perfect for minimizing new memory allocations. And I gotta say, I love this diagram. It shows such a clean, layered architecture, clearly inspired by Kotlin X Collection's Immutable. You can see at the very bottom, we've got the internal tree-up priority list. Then, layered on top of that, you have your clean, immutable, persistent interfaces. Off to the side are the builder APIs for doing efficient batch updates. And then, sitting right at the top, the star of the show, our concurrent priority queue, which orchestrates all the thread-safe magic. Okay. Now for the really fun stuff. Let's break down the core mechanics. How does an element actually get into this thing, side by side with other threads, with 0 locks? This right here is structural sharing in action, and it is beautiful. Look, when we insert the element 15, we are not copying the entire tree. We only create new nodes along the path from the root down to where our new element lives. That's the orange path. The rest of the tree, all those blue nodes, are completely untouched and shared. They are literally the same objects in memory. To put that in perspective, for a tree with, say, 10,000 nodes, an insert might only copy about 13 of them. We're sharing the other 9,987. That is a 99.8% reduction in allocation. It's huge. Now, after we insert a new node, there's a chance we might mess up the heap property. You can see it here. The new node 15 has a higher priority than its parent. We fix that with a simple rotation. But this isn't just any rotation. It's what's called a fused rotation. We copy the node and perform the rotation in a single atomic step. It's a clever little optimization, but it adds up, preventing temporary object creation and keeping everything lean and mean.
And this diagram perfectly captures the lock-free dance. You've got coroutine 1 and coroutine 2. They both start by reading the same initial state. Let's call it V1. Coroutine 1 finishes its work first, and it successfully uses a compare and swap operation to update the state to V2. Now, when coroutine 2 comes along and tries to do the same thing, its CAS fails because the state it started with, V1, is stale. But does it block? Does it wait? No. It simply says, oh, okay, rereads the new state, V2, recomputes its change, and succeeds on the next try. No locks, no waiting, the system just keeps making forward progress. It's fantastic. All right, so the theory is sound, it's elegant, but how does it actually perform out in the wild when things get really heavy? Let's check out the benchmarks. Well, the numbers pretty much speak for themselves, don't they? In a benchmark running 100 million add-all operations on a bounded queue, this library is just shy of 10 million operations per second. Now compare that to ConcurrentSkipListSet from the JDK, a very respectable library, which clocks in just under 2 million. That is a massive, massive difference in throughput. So where is that 5x speedup coming from? What's the secret? It's all about the bounded eviction fast path. See, once the queue is full, if a new element arrives that has a lower priority than the worst element already in the queue, it's just rejected immediately with a single comparison and zero memory allocation. ConcurrentSkipListSet, on the other hand, has to go through its whole insertion process every single time, only to maybe remove the element later. It's all that wasted work that adds up.
This table really just drives the whole point home. Yeah, sure, add is O of log n for most of these, which is what you'd expect. But look at contains key. For our queue, it's constant time, O of 1. How? It's backed by an internal persistent hash map. And then look at that bounded eviction row. It's just automatic. It's built in. For everything else, it's a manual, expensive process. And of course, the big one at the bottom, the concurrency model is truly, genuinely lock-free. Now, a data structure this powerful isn't just for being a simple queue. It unlocks applications that you might not even think of at first. Let's talk about one of the most exciting ones, on-device vector search. So, I'm going to ask a kind of provocative question. For a lot of use cases, especially on mobile, with small to medium-sized data sets, do you really need a heavy server-side vector database like Pinecone or Weaviate? Could you just use a priority queue instead? Well, the answer is a resounding yes, and this is exactly how. Let's take this type-ahead search example. A user types something, we tokenize that input into a sparse vector. Then, we just iterate through our candidate documents, calculate the dot product to get a similarity score, and we feed that score into our concurrent priority queue. The queue is bounded to, say, a max size of 5, and it just automatically does the work of keeping only the top 5 best matches, kicking anything with a lower score to the curb. It's that simple. And the impact of this is just huge. You're taking what is normally a complex, expensive, network-dependent operation and turning it into a pure client-side solution. It works offline, it's instantaneous, and it has zero infrastructure cost. For mobile and edge applications, this is an absolute game changer. Okay, let's bring it all home. We'll wrap up by going over the formal guarantees this library gives you, and we'll distill this all down into the most important takeaways. These aren't just hopes or marketing claims. These are hard, formal guarantees. Your operations are atomic. They're linearizable. That CAS retry loop we saw means you get a no lost updates guarantee. When you iterate over the queue, you're working on an immutable snapshot, so it's completely safe from any concurrent changes. And the most important guarantee of all, the entire system is lock-free, which means it is guaranteed to always be making forward progress no matter how much contention you throw at it. If there is just one single thing you take away from all this, let it be this idea. Randomness replaces complexity. That is the beautiful core insight of the Treap. It's what makes it possible to have a data structure that is simple enough to reason about, persistent enough to be ridiculously efficient, and powerful enough to solve some of the hardest problems we face in concurrent programming. It really makes you wonder, right? What other complex problems out there could we solve just by embracing a little bit of randomness?